Good morning. I'm going to talk about the reasoning architecture and services as related to data and reasoning fabric. As you know, data and reasoning is a big part of the DRF or the data and reasoning fabric. So let me take a few slides to talk about the reasoning architecture and the services in the context of the GPMA or the Greater Phoenix Metro Area. Okay, so the field test that we plan to conduct from January to March of next year in the Phoenix metro area is to demonstrate data and reasoning fabric as an architecture that works to really help metro areas to do many services. In this particular case, we have looked at a medical device being delivered on demand from a city center location to a rural area, specifically in this case from Mayo Clinic to Casa Grande in a rural area. And as part of the demonstrations, we are going to showcase that we can work all in software as services with the air traffic management, the city, and several other partner based services coming together to fly a drone vehicle autonomously from point A to point B. Now, we'll also show that many AI based decision support systems, which we call reasoning services, are used in achieving this goal. So, one of the first things that we have to think of is the corridor route that will be flown by the vehicle. Now, these routes have to be designed in a way not only a vehicle can fly, but also with the least disturbance to the metro area. So, we specifically choose 500 feet with about 200 feet altitude width and flying over either a freeway or river base so that avoid populated areas. So this, as part of the kind of the pre-planning effort that is done for many cities, in this particular case for Phoenix. So once this is available, we can now come up with episodes, what we call episodes, or different field test approaches. The first episode will be looking at DRF working with the vehicle and the services to fly the vehicle autonomously. Then we plan to integrate all of that with the airspace management system and the wind service. So there's one level of complexity added to the system. And in episode 2, we'll work with the city to come up with contingencies that could arise, for example, a rope drone or a weather service outage, or even a bad weather system, or a calm outage that could be caused by a tower, a communication tower failing, or the power failing, or any other problems. So these are episode 2 is more focused on the integration with the city services. I will now take you through some of these examples by showing how the reasoning architecture comes together for this particular application or test case. So let's look at episode 1 and look at the reasoning service flow. So in the middle, there's an operator. The main idea behind an operator is a supervisor who's in the middle of assigning the services, coming up with all of the needs for the vehicle to fly autonomously. So in the green, we have the supplier on the left who requests a delivery, either a phone call or it could be a software that tells the operator there is a request for a medical device delivery. The operator then looks at the starting point and the end point, or takeoff and landing, sends that information to the airspace volume service. So this service actually takes that input and comes up with a route. Like I said earlier, the route is designed to fly over either freeways or riverbeds. And once the volume service comes up with the route, it submits to the airspace management software. In this case, it's designed by NASA. PSU and DSS. Now, the role of this management software is twofold. One is to make sure this request can fit into the traffic that already exists, and also to be aware of the traffic that is ongoing so that these approvals can be made in real time. All this is done as a service. Once it's approved, the volume service comes back, tells the operator. Now that is step one. So all of this has to happen in the background. Once the service is approved or the operator is aware of the volume being approved, he sends that information to the trajectory service. So the trajectory service actually takes the input from the operator in terms of what vehicle that will be flown and stitches a trajectory that can be flown by the vehicle in the midst of weather, which is basically wind conditions, and also understand the battery health. So the operator now is completely aware of how long it will take, whether trajectory can be flown, and how much battery will be used. With this information, the operator, when satisfied, sends the trajectory to the aircraft. So once the aircraft gets the trajectory, it is ready to fly. Now keep in mind this aircraft is completely autonomous, so there is no pilot on board, but the operator is actually visually observing the vehicle being flown. In our case, we have simulated this using a high fidelity NASA simulator along with a drone that is really futuristic in the sense it can be flown as an air taxi or as a cargo delivery. So once the aircraft is ready to fly, it sends the telemetry data back to the operator, which the operator will broadcast so that it can be received by the airspace management software. So now let me briefly talk about the user interface we have for the operator. On the left, you see the Phoenix metro area displayed, and on the top, there is a button shown by the blue arrow. Once the operator clicks that, he gets into a DRF interface and registers for the services the operator needs. And once the services are registered, he gets an endpoint, and those endpoints are then used by the software to invoke the services. So in the next slide, you see the blue arrow showing how the operator selects the airspace volume service. So the volume service then returns the route that's shown there. And once the route is chosen, the operator then selects the trajectory and the battery available. And the trajectory is shown within the volume as the red line there. And once the operator is happy with the trajectory received, sends it out to the vehicle. And then the operator can also monitor the progress of the vehicle because of the telemetry data. So now you can imagine this repeated for 10 different vehicles. So the operator will have a complete view of the Phoenix area. So this is one of the nice things about having an operator. The operator can really manage multiple vehicles, look at the contingencies and so on. So we'll talk about some of the contingencies in a minute. But before that, let me briefly show you the actual simulated vehicle. There's a helipad on the left where the vehicle takes off, and the progress of the flight can be seen on the right. So this could be theoretically done using real drones. That is one of the future endeavors that we'll take on. Now let me talk about the contingencies that may come up, and this is where the city comes in. So the Phoenix as a city might have a civic policy engine. Our partners in Phoenix created that. So basically this policy engine divides the metro area into several polygons, and each of the polygons have a description of different contingency that may come across. Maybe a no-fly zone because there's a ball game going on, or there's an incident, maybe a rogue drone, or there could be a calm outage, and so on. So let's look at how the whole thing comes together. So once the engine triggers a polygon as a problem, the incident notification service takes that, figures out that polygon is in the route that the operator has chosen to fly, lets the operator know that there is a no-fly polygon. Once the operator knows that, he goes back to the volume service and initiates a complete change in the route, and similarly the trajectory in the battery health. Once the operator is happy with that change, and this can happen as the vehicle is flying. So this has to happen in real time, implying the communications have to be pretty quick in real time. And the operator takes that and sends it out to the aircraft. So this is one of the big contingency that may happen. So as you know, weather service is a service provided by a partner, and it is potentially possible any service could go down because of various problems that one could envision. If there is a service outage, DRF provides a way to switch to another service in real time. And that's the idea of this test, where the weather service outage is notified to the operator. Then the operator goes to the core catalog, DRF core catalog, and chooses another service. And the new service is provided. So this will be a good test of can you in real time switch services in flight. The third one is a very interesting one because we do depend a lot on the speed of communication for our real time operation. So the city is always looking out for failures in communications that could be due to power failures in the tower or some other disturbance. Once that is known, that is notified to the operator, and the operator actually signed on to this service, the notification service. Once the operator is aware of it, he goes back to the service manager and says, can you move your service? For example, if it's a wind service or a trajectory service, you don't want to be anywhere close to the tower where the communications have failed. Then the service manager will go to the core, DRF core, request a migration, and this will be discussed in another conversation, but the core will then take that, go to the communications health service, get a new, what we call an edge location or a new tower location for the service to move, and move the service. When we say move the service, it's a piece of software that will be moved to a different tower, and then the endpoint of that service will be provided to the manager, who will then communicate to the operator. So all of this has to happen in real time, and this is another test of the notification service showing us some of the contingency options and how we handle it. Okay, so to wrap it up, we have two episodes, many services, partners in the city, industry, NASA, and airspace management. And all of this are brought together to showcase the potential of DRF, how it can enable future flight, autonomous flight in metro area. Thank you.